Afternoon, everyone. So my piece of the Gabriell puzzle is focused on damage to buildings, which previous presenters have talked about the stress of producers from losing crops. A lot of these people have lost their homes as well, so it's quite important for us to understand what the driving damage processes are for buildings and flood events, and events like Gabriell offer the opportunity to do that. So just from a building research perspective, why was Cyclone Gabrielle an important event? One is for New Zealand, the scale. So with sort of major flood events in places like Australia, the United States and Europe, you will have potentially thousands of buildings that have been damaged. In New Zealand, that's quite rare. Most of our flooding is really localised. So we tend to get tens or maybe hundreds in a major event of buildings damaged in a flood event. Whereas in the space of 2 weeks, we had thousands of buildings damaged from Cyclone Gabrielle across Hawke's Bay and Tairāwhiti regions, but also from the Auckland anniversary floods, there was also another event that caused thousands of buildings to be damaged. So, and also these buildings were damaged across multiple regions as well. So again, usually we have localised building damage, whereas in this event, the building damage was very extensive spatially. One of the other reasons for its uniqueness was the intensity of the hazard. So in our research, we've been out to over 900 buildings across six major flood events in New Zealand, and I think the highest water depth at a building location we had recorded was 1.8 metres. So having floodwaters up to ceiling level or up to roof and above level is actually quite rare. It doesn't happen all the time in New Zealand, but there were many instances, particularly in the Hawke's Bay, where this type of flood hazard intensity occurred. Also, coupled with that is the range of different flow velocities, so really high flow velocities in places that caused scouring of land, but also the debris that came down with the floodwaters. So having metres of sediment piled up against houses was something that we don't really see that often. And also, a lot of the buildings were damaged in rural areas. So while building damage from flooding in rural areas is not uncommon, to the extent that it is uncommon. And also, I guess proportionately, in terms of historic flood events in New Zealand, we have large numbers of buildings damaged in urban areas and lesser amounts in rural areas as a volume. So it provides a good opportunity to, events like this provide an opportunity to see what happens to different types of buildings in terms of damage in rural areas. Right, so the reason for doing a building damage assessment is that it provides that real world view of what actually happens to a building when it's flooded. So we can simulate flood damage to buildings analytically and lab experiments, etc. But this is what actually happens. So it provides that opportunity to look at what are the driving processes for building damage. So in undertaking a building damage assessment, we're interested in a couple of different pieces of information. One is the hazard intensities at the building site. So what are the characteristics of the flood that may lead to damage of different levels to different types of buildings. There's the building characteristics. So these are the physical properties like the structural frame, the foundation type, the number of stories, and also the non-physical. So this would be characteristics like the building age. So the building characteristics coupled with the flood hazard intensities enable us to build relationships between these potential factors leading to damage to a building. And then we also are interested in collecting a damage level for the building as well. So this provides the dependent variable which we can then relate these variables to and build a damage model. And one of the reasons for building the damage models is that we can then use them in flood risk analysis. So once we've developed a model for different types of models for different types of buildings, we can then apply those in a flood risk model to then calculate for other areas if flood hazard intensity of X occurs to building characteristic of this, then we can then make a prediction of what the damage may be. So our flood damage data collection from Gabrielle happened in 2 phases. The reason being is that immediately after the event was really not the time to go into the field and start asking people about damage to buildings. Not only do people need that extra stress, but it's also, there's any number of hazards on site at the time, and also not to be in the way of any sort of recovery process. So, and also access was an issue. So for instance, Wairoa, you had to get there by a flight rather than, you couldn't drive up there, for instance. So we implemented our damage survey in 2 phases. One was a survey in Wairoa in April after the event. And this was a building by building survey across the town. And then a later survey in October 2023, and this focused more on Hastings District, Napier City, so Esk Valley type area, and Tairāwhiti region. In general, these types of surveys aren't undertaken 6 months after an event, but given the scale of damage and a lot of damage being in situ, there was still the ability to go out into the field and survey damage to buildings. So in terms of the data collected, we had to, because we couldn't get out on site immediately in the October survey campaign, we rely on modelled representations of flood hazard intensities. So this is the work that Emily just presented. We're able to marry up the flood hazard intensities from the hydrodynamic model to building locations to come up with those variables. Through the on-site surveys, we were able to collect building characteristics and also estimate a damage level to the different components of the building. So being the structure, the external finishes, internal finishes, and the services. So just some observations from the damage data collected. So we had over 1,200 hazard intensity samples for each building that was surveyed. So basically a sample for each building surveyed. What's interesting about the data set compared to other New Zealand flood events that we've surveyed has been the number of buildings that were flooded by more than 3 metres of water. So this is getting up to that sort of ceiling level, rooftop level for buildings. So we have over 150 buildings that were flooded by more than 3 metres of water. So this is really providing information about damage to buildings that we haven't seen before through recent events. We also had really high flow velocities at a number of sites, so greater than 2 metres per second. So that's getting into the potential where you might expect to see some damage to the external finishes and even maybe the structural frame, particularly if there's debris loading. And also a variable that we're able to bring into this data set through the flood hazard modelling was momentum flux. So this provides an indication of force on the building as well, which might be useful for relating to damage. Regarding the buildings themselves, the highest, quite a large proportion of the buildings were residential, which is not uncommon from a New Zealand building stock perspective, and also structural frames constructed of timber, which is pretty common across New Zealand. So but we also were able to collect a large number of samples related to buildings used for rural purposes or production purposes, which is something that we haven't had in the past. We're able to join information about the land cover at the building site. So Emily mentioned roughness as a variable in a flood model. Land cover can bring in a variable that enables us to analyse perhaps what the land cover may have influenced in terms of the building damage. And then the final piece of information that we collected was the damage levels to the buildings. So most buildings fell into a damaged but repairable state, but then we also had over 300 buildings that were observed that had damage to components that would be deemed unrepairable. So again, usually in other New Zealand flood events, we tend to have mostly repairable damage, whereas in this flood event, there was a really large proportion of buildings that were not really repairable. So what we do with this information now is that we can convert, we've got multiple variables on flood hazard intensities, building characteristics, and a dependent variable being the damage ratio, or the proportion of the building damaged, which we can then start to play around with machine learning algorithms to predict, to look at these variables and try and form a predictive model based on what we've collected for the event. So what we've done here is we've looked at different regression-based machine learning algorithms that represent decision trees. So we've selected 4 out of a large range. Decision trees being a deterministic model, so basically you get a single realization from one decision tree. And then random forest, extra trees, and extreme gradient boosting being an ensemble model where you're creating an ensemble of decision trees to form a damage prediction. So in selecting these models, we can play around with the parameters and then tune the models to try and optimize the prediction. So here we can see that the extreme gradient boosting model provides the best prediction overall due to the closeness of the predicted points to the identity line on the graph. So then what we can do with that model is that we can take it a step forward and start to look at what the damage drivers are. So the nice thing about the decision trees is that they also provide some analytics around what variables in the model were having the greatest influence on damage. So with our trained extreme gradient boosting model, we're able to look at what variables were used in the model learning to form the highest predictive accuracy. What's different here from other flood events that we've observed around New Zealand is that the primary use of the building stood out as a key variable that was important for damage. In other flood events around New Zealand, this hasn't really had much of an influence. So this was something that was of interest. I'm not quite sure why, given that we had a large proportion of residential buildings. And I guess that might mean that some of these other variables related to the hazard intensity might mean that hazard intensities may have had a greater influence on the potential for residential building damage. One other uniqueness of this data set compared to other flood events was that floor height had very little importance on flood damage. And I guess that could be explained by the depth of water that was observed at building locations. So in an urban environment, floor height is really important for determining whether a building's damaged or not, and that's because you generally have lower flood depths, whereas in these environments, the flood depths were at a magnitude that floor height showed no importance, really, in terms of the damage outcome of the buildings. So from a risk modelling perspective, that's really useful because that means that going out and collecting floor height data is a really expensive exercise. So perhaps you can ignore that if using these models with like the flood maps that Emily's group's created. The other thing we can do is look at how introducing different variables to the model affects the model performance as well. So going out and collecting variables, again, is a resource-intensive exercise, so the fewer variables that you can collect to come up with a good predictive outcome is ideal. So what we've done here is that in taking the variable rankings from highest to lowest importance, we loop each one through the model and then look at how the predictive performance changes as we add more variables. So we can see that the model performs most optimally with the addition of water depth, which you have to have because there's a flood, and the primary use variable. So those two, the one variable that's required plus the one that has the highest importance creates potentially the best predictive performance of the model. And then we can see that up to 5 variable additions, the model still remains stable, and then it starts to overfit thereafter. So introducing some of those variables to the model that may be of less importance can actually confuse the algorithm and lead to a less optimal predictive outcome. We can also see that from the model that there's with the mean bias error, the panel on the right, that there's the model is actually under-predicting a lot of the time. So, so what that potentially suggests is that we may be confusing the model with having a really broad range of flood hazard intensities being considered for prediction, and we may need to look at spatial clustering for places like, say, Pakawai or Esk Valley, and maybe relearn the model to predict damage specific to these spatial clusters in order to optimize the model result. So just in terms of further research, there's the potential to extend the variable range with some of the products that Emily's just presented. So the differential maps to represent where sediment was deposited at building locations could be another variable addition to the model, as well as analysing where scouring and other secondary hazards happen and bring those into the model as well. After the event, the territorial authorities do rapid building damage assessments. So these are the placard type assessments that are carried out immediately after a flood event. I think there's the potential to bring that information into the model as a variable, and what that would potentially mean is that with a trained damage model that has the building placard data as a variable, we could potentially use these models immediately after flooding as placard data is being collected, and then we could bring that into the model and then provide a prediction of what the damage is to the building. So that would provide a more sort of rapid understanding of what the physical damage to buildings may be as soon as that data is collected after a flood event. As mentioned, I think there's probably more to the story, and investigating the use of spatial and temporal clustering techniques to fine-tune models to a specific location is something that would be really useful to look at, particularly given that the data set has quite a large number of buildings across a really broad spatial area that would support that type of analysis. And then with these trained building damage models, we can then start to use them in impact models for flood events, as well as risk models to calculate what the annual expected damages are from flood events, in particularly Hawke's Bay and Tairāwhiti. They can be used also for what-if type scenario analysis. So, dare I say it, what if a stop bank breached on the Tairāwhiti into Napier City? This type of model could be used as part of the impact model to calculate damage to buildings. And then as part of that, what if we constructed the stop bank up to a certain level that would stop that type of event from happening? These models could be used to provide part of the economic analysis for cost-benefit analysis as to whether specific mitigation interventions may pay off economically over time. Thank you.